Welcome to Visual Algebra Lecture 5.5, Actions of Automorphisms. The automorphism group of any group naturally acts on the group itself, and also on the set of conjugacy classes. In this lecture, we will look at this and related actions of the inner and outer automorphism groups. The full automorphism group also acts on the subgroups of G, and the orbits are at least as coarse as the conjugacy classes. The fixed points are called characteristic subgroups, and this is stronger than normality. Examples of characteristic subgroups include the center, the commutator subgroup, and several new subgroups that we'll see this lecture, such as the Frattini subgroup and the socle. We'll interpret and explore these in terms of some of our favorite subgroup lattices. So let's get started. For any group G, the automorphism group of G naturally acts on the group itself in the way you would expect. So we have a homomorphism from the automorphism group to the permutations of G. And when we press the sigma button in our group switchboard analogy, then that's the permutation that sends each element to sigma of G. Let's see an example. Any automorphism sigma of Q8 must send I to an element of order 4. So there's 6 choices, plus or minus I, plus or minus j, or plus or minus k. Once we decide where I gets sent, then we have 4 choices for where j gets sent, because j cannot get sent to the same place as I, or the negative of it, if we want this to be an isomorphism from Q8 to itself. So in other words, if I gets sent to k, then j has to get sent to either plus or minus I or plus or minus j. This means that we have at most 6 times 4, or 24 automorphisms of Q8. I'm not saying that we have exactly 24, just that's an upper bound. We studied inner automorphisms at the end of chapter 4, and recall that we always have, for any group, G mod the center is isomorphic to the inner automorphism group of G. So for Q8, the center is generated by -1, so Q8 mod the center is isomorphic to V4. So we have a bijection between inner automorphisms and cosets of the center. So here are those cosets, which means that we have 4 distinct inner automorphisms, conjugating by 1, conjugating by I, conjugating by j, and conjugating by k, these elements here. And this group is isomorphic to V4. Inner automorphisms, by definition, preserve conjugacy classes. So they permute elements within conjugacy classes. Now, there are 4 inner automorphisms, and there are, I claim, up to 24 automorphisms, and actually I'll show you that there are exactly 24 automorphisms. Can you think of an automorphism of Q8 that is not inner? Well, there are 6 permutations of I, j, and k, and each of these defines an automorphism. So these permutations define a subgroup of the automorphism group, which we will call H. Only one of these is inner, that is the identity permutation, because for all others, we are permuting conjugacy classes. Now, the inner automorphism group is always normal, something we proved in chapter 4. I might have left it as an exercise, I don't remember. And the intersection of this subgroup with these permutations is trivial. So N intersect H is only the identity permutation, because, again, these are all permutations of I, j, and k, and all of these inner automorphisms act trivially on these conjugacy classes. So that means that the automorphism group is a semi-direct product of N, which is the inner automorphism group, and H, which is isomorphic to S3. So this is a semi-direct product of the inner automorphism group with the outer automorphism group. Remember, the outer automorphism group is not the outer automorphisms, because there are 20 outer automorphisms. Let me just write this down. Remember that the outer automorphism group of Q8 is the quotient by the inner automorphism group. So you can think of how many, so this is saying how many automorphisms are there up to conjugacy. The idea is that there are 6 truly distinct automorphisms up to conjugacy, all these permutations, and then once we do one of those, we can conjugate to get the rest of them. So the automorphism group of Q8 is a semi-direct product of V4 with S3, and that's not obvious, but that is isomorphic to S4. One reason for showing you this example is to warm you up to these ideas that we saw at the end of chapter 4, but also I want to kind of merge them with this group action framework, which is the subject of chapter 5. So the automorphism group of Q8, which is, by the way, a really good example to illustrate this, naturally acts on the set of elements of Q8, as we've seen. So we have this groups switchboard up here, this massive thing, which has the identity. So it has a button for every automorphism. It has conjugating by I, conjugating by J, conjugating by K. This really is the inner automorphism group. And then there's 20 other automorphisms as well that are outer. So remember, we have a subgroup consisting of all permutations of I and J. Let me write down buttons for that. So say swapping I and J is a button. Swapping J and K is another button. And then the others I'll just write in black. I don't know what other colors to. So swapping I and K, and then cycling I, J, and K, and cycling I, K, and J. So here's a subgroup of size 6. Here's one of size 4. And then the other elements are going to be just compositions of these things with these things. I think you can actually, you could write cosets. You could look at the cosets of this by just subgroup of order 4 by just multiplying by these things down here. Or you could look at the cosets of this by multiplying by these things here. Remember, this is the normal subgroup. So just to, I'm not going to write all of these, but you could conjugate by I and then swap I and J. Or you could conjugate by I and you could swap J and K, and so forth. So where were we? So this group acts on these 8 elements, and here is that action graph. So when you press one of these buttons, and let me just clarify. So this is the inner automorphism group of that right there, which I called N on the previous slide. And then this subgroup here, I don't know if I have room to write at the top, but this subgroup here is H. So when you press one of these buttons, when you press the, maybe I should denote these in colors to match the colors that I'm using below. So when you press the phi I button, when you conjugate by I, you follow the red arrows here. When you conjugate by J, you follow the blue arrows here. And when you swap I and J, you follow the purple arrows. And swapping I and J is going to force K to go to negative K. I'll let you work that out on your own. And so forth. So this is the action graph of this acting on Q8, but it also naturally acts on the conjugacy classes. So this is a different homomorphism. And when you press the sigma button, the permutation just sends the conjugacy class containing an element to the conjugacy class of wherever it gets sent. So here is the action graph of that. So this acts on elements and also acts on conjugacy classes. Notice that the only arrows that go between conjugacy classes are the ones corresponding to the outer automorphisms by definition. There are also actions by the inner and outer automorphism groups, but we have to be careful about what these act on. The inner automorphism group is pretty safe. So that acts on the set of elements just as before. If the entire automorphism group acts on G, then a subgroup of it will as well. And here is that action. Now the outer automorphism group, remember the outer automorphisms are not a group themselves. This is, to remind you, it's isomorphic to Q8 mod the inner automorphism group. That does not, it's tempting to draw this diagram and say, hey, look, this acts on the group as well, right? And then you just overlay these things and you get the thing that we got before. But got to be careful, that's technically not right. And to see why, let's go back and sketch our switchboard. I'm not going to draw the entire thing, but let's put the identity and the three inner automorphisms, or the three other inner automorphisms, and then let's do the permutation ij, the permutation jk, and then the other permutation. So there's ik, and then there's ijk, and then there's ikj. Well, I have a little bit of extra room here on the end, but that's okay. So this is the inner automorphism group here, as we saw before. And then this group here, how about if I put this here, and then I will do my eraser and just get rid of this. And this group here is H, which is isomorphic to S3. So the inner automorphism group, or the outer automorphism group, is isomorphic to this H. So this is isomorphic to the outer automorphism group of Q8. So the elements of that are the cosets of the inner automorphism group. So let's draw these cosets. So here, so the outer automorphism group really consists of these cosets right here. And so what does this mean here? So why does this not act on the elements? Well, there is an element ij that sends I to j, but then there is, keep forgetting to do this, so I'll add these colors. But if I compose that with this inner automorphism right here, where I conjugate by j, so let's, ij doesn't really matter which order we do it in. I mean, we will get a different answer, but for the purpose of this, so if we apply this automorphism and then we conjugate by j, we will send this thing down to there. And so here's a different element in that same coset that doesn't send I to j, sends I to negative j. So this particular coset is ij times h, and that's this entire coset. And when I press this button, well, where does this element go? If I press this button, it goes here. If I press this button, it goes there. That's not well defined. So it's really tempting to make this diagram. And I did it first thinking it was true, not realizing it was a mistake, and say, well, the outer automorphism group acts on this, but it does not. It acts on the conjugacy classes. And the action graph for that is a lot like, let's draw it. So the conjugacy class containing, there should be a 1, the conjugacy class containing -1. There's the conjugacy class containing I, and these should be conjugacy classes. I'm just drawing the individual elements. And so this orange, so I think you see how this is going. It will swap those and it will fix that. So this group acts on the conjugacy classes. This group acts on the group. It also acts on the conjugacy classes, but it does so trivially because it fixes all of the conjugacy classes. So all of the buttons are broken. But both of these groups will act on the set of subgroups of G. So think about what that is. So if the inner automorphism group acts on the set of subgroups, that means that we are conjugating subgroups, and that's something that we've done before when we've constructed subgroup lattices. Now the to have the outer automorphism group or the full automorphism group act on the subgroup lattices, that is going to merge non-conjugate subgroups together that we have not done before. But I'll show you that on the next slide. A subgroup H of G is characteristic if it's preserved by all automorphisms. This is not that common of a term. Like, it's not something that you'll see in every intro group theory class like you will normality. So there's no one agreed upon symbol. Ones that I've seen include just CHAR or char, and I think I've also seen CH, but I've also seen a normal subgroup symbol that's filled in like this. So this is a stronger condition than normality. And the reason why I did not put a symbol like this here is because that is not built into the LaTeX typesetting language. Examples of characteristic subgroups are the center and the commutator subgroup G prime. Normality of subgroups is not transitive. That is, if K is normal in H, which is normal in G, that does not imply that K is normal in G. Can you think of a counterexample? There's a lot of them. Here's a basic one. The subgroup generated by F is normal in the subgroup generated by R squared and F because it has index 2. And that's normal in D4, which has index 2, but this is not normal in D4, as we know. So of course this cannot be true. If it were in general, then anytime we had a group of order 8, 16, in general 2 to the n, every subgroup would be normal by repeating this argument. And of course that's not true. However, being characteristic is transitive. So if K is characteristic in H, which is characteristic in G, then K is characteristic in G. I'm going to leave that as an exercise because this is one of those side topics that's fun to explore, but it's not really crucial toward the rest of the class. Sometimes it is helpful to see a subgroup diagram variant where the nodes are something called automorphs instead of conjugacy classes. And let me explain this and do an example. So conjugacy classes are the orbits under the action of G by conjugation, whether that's elements or subgroups. Automorphs are the orbits under the action by the automorphism group. So here is the group D6, and let me draw a hexagon. So D6, there are 6 reflections, and remember 3 of those are conjugate. These are the so-called side bisecting reflections. This is R squared F and R to the 4th F. And then 3 of them are the so-called angle bisecting reflections, and these are conjugate. So this is RF and R cubed F. So let me mark those here. Say those are the side bisecting ones, and these are the angle bisecting ones. And then the V4 subgroups above are what you get by taking 2 orthogonal reflections, one of these, one blue one and one green one, and that's going to generate a V4 subgroup. So I'll circle it like this. One of these D3 subgroups consists of 3 blue reflections and then 120 rotations, or generated by the 120 rotation, and this one consists of the other one. So the group D6 acts on its subgroups by conjugation, and these are the orbits, or at least I've circled them, and we can construct a so-called subgroup diagram where we've seen this before, where the nodes are the orbits. So the nodes are the conjugacy classes, and anytime there's a non-normal subgroup, that means a conjugacy class of size bigger than 1, we put a subscript on the left to say how big it is. Something else we can do is construct a so-called automorph diagram. So there's an outer automorphism that sends, I think I called it W or omega in an earlier lecture. on inner and outer automorphisms that sends F to RF. So you can think of this just as rotating the labels on these axes. Like, it doesn't really matter which one we call F. I call it this one, but you could call it a different one. So this is an outer automorphism. And when you do that, that is going to send one of these subgroups to one of the other subgroups, and etc. I don't really know which the order of these things. Well, that's going to so this is an outer automorphism. So when the whole automorphism group acts on these subgroups, it's going to merge this into a single automorph class. So all of these are in the same orbit. So we put a 6 here. This doesn't change, but now these two D3 subgroups, since there's an automorphism that sends these blue reflections to the green ones, those get merged into a single automorph class as well. So I don't know what to call this. I guess automorph diagram seems simple. Subgroup diagram is my own term. This convention is used in group names in the LMFDB. I really like it. They call it subgroup lattice because it really is like a concise way to call it. It's like a reduced version of a lattice, but it need not actually be a lattice. As we take S5, an example that we saw earlier. So I like to use the term diagram to emphasize that and to distinguish it from this. And I think automorph diagram is a fair version of this as well. If you go in the LMFDB, there's a box where you can click like nodes are conjugacy classes or nodes are up to isomorphisms. And so you can actually view this for any of the groups, just like how you can view this. Oh, let me mention one more thing quickly before we move on. The nodes over here that do not have left subscripts, these are the fixed points under the action of conjugation. They are the normal subgroups. The nodes over here that do not have a left subscript, those are the fixed points under the action of the automorphism group. Those are the characteristic subgroups. So that's why I say this is a stronger condition than just normality. A few slides ago, I introduced the notion of a characteristic subgroup. That is a subgroup that is invariant under all automorphisms. I mentioned that the center and the commutator subgroup were two examples for any group. I want to show you two more subgroups that are characteristic. Here, for the first one, I need to define the notion of a maximal subgroup of G. This is probably exactly what you think it is. If you have a group here, a maximal subgroup M just means that there's nothing in between it. So you can say that. Here's an alternative way to formalize that. So M is maximal if it's a subgroup of G, and if there's any other H between M and G, then it has to either be M or it has to be G. So that just means that there's nothing that's properly between here. The Frattini subgroup, denoted phi of G, is the intersection of all maximal subgroups of G. This is a characteristic subgroup, and therefore it is normal. It turns out, I will leave this as an exercise, that it is the set of non-generating elements of G. And by that I mean an element is non-generating if any time it's included in a generating set, you can always remove it and the remaining elements will still generate G. Finally, if H and K are finite, it's a straightforward exercise to prove that phi of H cross K is phi of H cross phi of K. So I will do some examples of this in the next few slides. This is a topic that is often left for the exercises in a textbook, and I think for good reason. It's mostly going to be left for the exercises in my book as well. I think I'll mention it here, but there's a reason why I'm not proving these, because these are not crucial things to do. But it's important, I think, to define this, just to see other examples of characteristic subgroups. You might see this on the LMFDB, but also the notion of a maximal subgroup. While this is not, a too terribly important thing in intro group theory, a maximal ideal in the setting of rings is extremely important. So it doesn't hurt to sort of drop this definition early so you can think about what it means for something to be maximal. And then we'll come back to it in chapter 8 when we get to ring theory. And, I think we'll also see it in chapter 6 as well. Chapter 6, we will be climbing down subgroup lattices to construct what's called a composition series. And for that, we will need to start at the top of a subgroup lattice, find a maximal subgroup and maximal normal subgroup, and then go down there and continue that process. So it certainly doesn't hurt to see the definition here. Here's another definition. The socle, denoted SOC of G, is the subgroup generated by all minimal normal subgroups of G. And again, I will show you pictures of these in some subgroup lattices after this. If G is a finite solvable group, then the socle is a product of cyclic groups of prime order. Now, do you know why it's called the socle? I did not know what this word was. I had to look it up, but there is a reason for it. In architecture, a socle is a short little pedestal, like this thing down here, that supports a sculpture or a column. So you get this big subgroup lattice, you got these minimal normal subgroups. I didn't define minimal normal, but you can do it analogously to maximal normal. Then the subgroup generated by these is, I don't know, not always, but probably going to be something kind of small, this important small normal subgroup in the entire lattice. And so it's like this pedestal that supports this big giant lattice above it. Cute name. But you can find this on LMFDB as well. Let's do an example of a familiar subgroup. This is the semi-direct product of Q8 and C9, and let's compute its center, commutator subgroup, Frattini subgroup, and the socle. So the first thing to do is let's circle the normal subgroups. We can identify anytime there's a subgroup that is unique of its order, it has to be normal. So these have to be normal. And then by the correspondence theorem, we can tell that these subgroups are not normal. So if we quotient out by this, recall this is the lattice of A4. We know that these are conjugate, and let me mark those as well. So we know that these are conjugate, and we know that these are conjugate. And I think you can, if you look up these quotients, you can deduce that, well, actually by the single parent property, we can deduce that these have to be conjugate as well, and these have to be conjugate. Okay, so the maximal subgroups, let me mark those. Those are this and these things. So the intersection of the maximal subgroups is this C6 right here. So this is the Frattini subgroup of G. So we did that one. The socle, this is generated by the minimal normal subgroup. So here are two minimal normal subgroups. Those will generate this. So this is also the socle of G. The commutator subgroup. So commutator subgroup is going to be one of these normal subgroups. Which one is it? So this mod this is C3. This mod this is order 9. This is C9. This mod this, well, that's A4, and this is even bigger. So this is going to be the commutator subgroup, G prime. And then what's left is the center. And, well, what can we say about the center? So the center, so there's a unique element of order 2. So that has to be central. So the center has to contain C2. It cannot be Q8 because we know that's not central. So the center is either this one or it's that one. And honestly, I do not know by inspection a way to determine this. There might not be. You can't always tell what the center is from a subgroup lattice. And we know that because we've seen two groups of order 16 that have the same lattices. One is abelian, one's not. So I actually just now looked this up, and LMFDB, you go to this group. This group, by the way, is 72.3. That's the group ID. There's a whole bunch of groups ordered. 72, and it tells me that this is the center. So that, to me, means that these elements of order 3 have to be central as well. I don't know why that is. Maybe there's some weaker, so here we said that if there's a unique subgroup of order, well, we said any subgroup that's normal of order 2 has to be central. That's not true for a subgroup of order 3, but maybe there's some weaker argument we can make because there's only one of these or something like that. I don't know. Let me know in the comments if you see a way to do this by inspection. In chapter 6, we'll learn about ascending and descending central series, and it's something when we study nilpotent groups, and we'll be able to, in some cases, to use that to determine what the center is, because there's relations between these series. But that's for the next chapter. Here's our next example. This is the semi-abelian group SA₁₆. I don't think we've seen this lattice, but we've seen the semi-abelian group SA₁, and that lattice looked like this one. And that was the one that I just mentioned, where there's two subgroups of the same order that have the same subgroup lattice. So I can't actually tell from right away whether this is SA₁ or C8 cross C2. Now, if you're just tuning in for this chapter, we introduced semi-abelian groups in chapter 2, and we've seen them come up, I think probably definitely in chapter 3 and chapter 4. So it's one of our recurring examples, but it's not a common group because it has this weird presentation, but it's very natural when you look at the Cayley graph and some other properties of it. Okay, so what can we say about this? So the Frattini, well, let's circle the normal subgroups as we did before. These all have index 2. They have to be normal. These are all unicorns. They have index 4. This one's got 3 kids. This one has 1 parent and 1 kid. This one's got 3 parents, so they all have to be normal. We can make the same argument for here. These things are all unicorn subgroups. That's something from chapter 4 if you're tuning in for this. This also is the only order 2 subgroup with 3 parents. It's got to be normal. These things here, this cannot, if this were normal, it would be central. And then this group, SA₁, which is generated by R and S, would have to be abelian, and it's not, so that means that these things have to be conjugate. Okay, so the Frattini subgroup is the intersection of all of these maximal subgroups, so that has to be this subgroup right here. So that's the Frattini subgroup. What about the socle? So the Frattini, we did that. The socle, we take the minimal normal subgroups. Well, there's only one of them. And what do they generate? So this has to be the socle. What about the commutator subgroup? So we want to know how far can we go down this lattice, take a quotient, and get an abelian quotient. Well, G mod this subgroup is V4. G mod this subgroup, you should recognize that as C4 cross C2. G mod this subgroup, well, that's got that lattice of either SA₁ or C8 cross C2. But if you look at, by the correspondence theorem, all of these subgroups here are normal, particularly these two are when you take the quotient. So what that means is that this has to be an abelian quotient. It's got to be that one. So this is the commutator subgroup. Okay, so that is the commutator subgroup. What about the center? So this is one where, again, it's really hard and often it's not feasible to compute the center just by inspection of the subgroup lattice. So I looked it up in LMFDB. It tells me that the center is isomorphic to C8, and so that means that this is the center. And I also saw in LMFDB that this is actually this group right here. It's not that one. And so that tells me that R squared and S commute, which means that R squared commutes with S. And so that means that if R squared commutes with S, then R squared commutes with everything because it commutes with R. So this has to be the center. Another way that you could do this, and I don't see any way to do it by inspection. If you do know, let me know in the comments. I'd be happy to learn something. Sometimes there is like a way that you notice. Another way is to look at the Cayley graph, which is you can find, I have a whole lecture on semi-dihedral and semi-abelian groups in chapter 2, and you can just check in the Cayley graph that r squared s equals s r squared. Finally, I will say that actually I do know how to do this by inspection, but it requires the techniques that I mentioned in the previous slide that we'll see in chapter 6 about ascending and descending central series and nilpotent groups. So you'll have to wait for that one. Here is our last example. This is, I should say, a semi-direct product of C7 and C6, because I think there's more than one of them. This is also the affine general linear group of one-dimensional transformations over Z7. Remember, AGL₁ Z5 is a group that we've seen a lot that has order 20. So this is also sometimes called the Frobenius group, FR7 or just F7. Okay, so the normal subgroups, they're easy to identify. Every subgroup that's unique of its order is normal. And then in D7, these subgroups are all conjugate by the single parent property. These have to be conjugate, and similarly, these have to be conjugate as well. So the maximal subgroups, this and these, and also D7, those intersect trivially. So the Frattini subgroup has to be trivial. And so we did that one. We've also deduced that the center has to be trivial as well. Remember, we did that in chapter 4. And the argument is because G mod the center can never be a non-trivial cyclic group. And so if this were the center, G mod the center would be C2, or C2. Here it would be C3, and here it would be C6. So these can't be the center. So the center's got to be down here. So that's the center, the commutator subgroup. It's got to be one of these normal ones. And this mod that's a D6 quotient. So I think we also did that as well. So that's the commutator subgroup. And then the socle is generated by the minimal normal subgroups. So let's see, what are the minimal normal subgroups? That is a normal subgroup that is minimal. There's nothing in between it. And it's the only one because these things all have smaller normal subgroups containing them. So this has to be the socle. Okay, so that is the end of this topic. Moving on, we will look at equivalence of actions. So we'll see why every left action is equivalent to a right action, and what does it mean for two actions to be equivalent. So this is actually a weaker condition than isomorphism of G set, and we'll understand what that means. Basically, two actions are equivalent if there's a bijection between the sets and an isomorphism between the groups. So you can think of this as like rearranging the stickers via some group isomorphism in a way that the action graphs still have to be isomorphic. So that's actually a weaker condition than what it means for two G sets to be isomorphic. For that, you really need the stickers to not move at all. You need that isomorphism to be the identity. And that is not at all clear why we should have these different definitions, but we will explore that in the next lecture, actually in the next couple lectures, because after equivalence of actions, we will look at G set isomorphisms and G set homomorphisms. So that's really important. I hope you stick around.